Hello everybody. Let us try to understand the combinatorial optimization problems and how these problems can be implemented on quantum computing. What happens is that combinatorial optimization problems can be mapped to a Hamiltonian whose structure matches the classical Ising model. That means the Hamiltonian of the combinatorial optimization problems can be mapped to the Hamiltonian of the classical Ising model, the structure of the Hamiltonian of the classical Ising model. This allows the problems to be implemented on quantum hardware, where the optimization task becomes finding the ground state of the Hamiltonian. By using this mapping, the complexity of many hard problems can be reduced to energy minimization problem complexity, which the quantum computers can handle very efficiently. So all in all, what I mean to say is that many combinatorial optimization problems can be encoded as an Ising type Hamiltonian. This makes them suitable for quantum implementation, where the task is reduced to finding the ground state or the minimum energy state, often giving a more favorable computational pathway. So let us try to understand what are combinatorial optimization types of problems. So combinatorial optimization is the study of problems where you need to choose the best solution from a finite but enormous set of options. So therefore it becomes an optimization problem. What is the optimization problem? We are available with a finite but enormous set of options, that means solutions, and we have to choose the best solution. So therefore we have to optimize. Therefore these problems are referred to as the optimization problems because we have to find the best solution from a set of solutions. Now, these set of solutions which are available to us are usually combinations or arrangements of discrete items. So that is why these are called as the combinatorial, because of the combinations of discrete items in the solutions. So therefore, these problems are hard to solve exactly when the search space means from all the solutions available, when we have to find the best solution. So the solution space or the search space grows quickly and exponentially as the problem size increases. As the problem size increases, so we have to search a larger space, which becomes very difficult for classical computers to handle. So therefore, combinatorial optimization problems can be implemented on quantum hardware. The question is why the classical Ising model matters. The Ising model describes a set of spins which can point up or down. So these spins are basically, I'm talking about the magnetic spins. Each spin interacts with its neighbors and the total energy depends on these interactions. I will explain the complete modeling of the classical Ising model, that how the spins, um, uh, which basically means the interaction between the magnets, can lead to the overall Hamiltonian of the system that we will identify, that we will write, and then that Hamiltonian can be mapped to the combinatorial optimization problems, and we can solve some NP hard problems in computer science where the Hamiltonian can be mapped to the Hamiltonian of the Ising model, which is basically is describes the set of spins, right? Um, in physics, it explains magnetism. In computer science, it turns out to encode many difficult optimization tasks. The hard part is finding the spin configuration that gives the minimum energy. Ultimately, we have to find the minimum energy solution. Even in the classical Ising model, the difficult part is to find that spin configuration which gives the minimum energy. Now, for many interaction graphs, this is an NP hard problem, and that means there is no known efficient classical method that solves all instances quickly as the problem size grows. So this is definitely an classical Ising model is definitely an NP hard problem, but we have been able to model the Hamiltonian of the classical Ising model. So let us we will try to understand the modeling of the Hamiltonian in just a moment. Why the quantum computers become a natural playground? Because quantum devices can represent superpositions of many spin configurations at once. That's where the quantum advantage actually comes in the quantum devices, where the quantum devices can represent superpositions of many possible many combinations, right? Which actually present us the advantage of quantum parallelism. They can explore the energy landscape in ways classical systems cannot. This gives a credible motivation for using quantum algorithms to solve classical Ising problems, such as the problems, a lot of problems in computer science exist which can be solved by this mapping of the Hamiltonian of the problem with the Hamiltonian of the Ising model. Problems like max cut, graph partitioning, feature selection, routing and scheduling, portfolio optimization, protein folding approximation. These are some problems I have mentioned here, and there are many other problems which can be NP hard problems which can be solved using this approach. And all the problems reduced to energy minimization, they map directly to the Ising Hamiltonian. That's why they map directly to the Ising Hamiltonian, which is a big advantage which we have to actually understand. So therefore, I will start with the with modeling the Hamiltonian of the classical Ising model. Actually, I will do that using a different presentation. I will have to open that presentation in the same in the next in a separate window than this presentation which I am talking about. Let me just find out the PPT. I'll take a moment, please. Okay. So this is the presentation I am doing. So yeah, this is the classical Ising model, which in this presentation I will explain how the Hamiltonian will be modeled in this classical. What is classical Ising model actually, and how the Hamiltonian will be created. So let's look into the let's just okay. Now, in the classical Ising model, consider a spin system in which the spin defines a two-state system. So, it is a two-state, every spin defines a two-state system. Imagine that you have two magnets. Imagine we will start from two magnets, we will end up with many more magnets, but let us start from the from two magnet configuration. Imagine that you have two magnets fixed on the same axis. They will naturally anti-align. If the two magnets are placed side by side, they will naturally anti-align. Means if the north pole of the first magnet is upwards, for the second magnet the south pole will be upwards, like that. And let us say sigma 1 is the random variable which we use to represent the spin configuration of the first magnet, and sigma 2 is the spin for the second magnet. So if they anti-align, that means the product of the two random variables will be equal to -1. So it is sigma 1, sigma 2 will be -1 of the two magnets. Now let us introduce a third magnet here, and its spin is defined by sigma 3. So the third magnet will interact with the second magnet will interact with the first magnet. So two terms will come into existence. One is sigma 2 into sigma 3. This is the term, and the other is sigma 1 and sigma 2. Which is this sigma 1 sigma 2 term. Now, so you have two terms here, sigma 1 sigma 2, and the other term is sigma 2 sigma 3, because of the interaction of the magnets with its neighbors. So in general, we can consider more magnets. So the sigma I into sigma j represents the interaction of the magnets with their neighbors, and when all the interactions are summed over all possible magnets, this will give me the Hamiltonian H cap. That's now what is the aim? The aim is to minimize this Hamiltonian ultimately, to find the best spin configuration, right? Now let us complicate the matter a little further. We place certain magnetic bars in between the magnets. What these bars or walls will do? They will control the strength of interaction between the two magnets. For example, if this bar is there, this will control the interaction between the first and the second magnet. The second bar will control the interaction between the second and the third magnet. Right. So let us say we define a coefficient j subscript ij, which actually describes the which actually defines the coupling between the two magnets. So we model the coupling using this coefficient jij with each of the pair of interactions as given below. So overall, Hamiltonian now becomes h cap becomes summation of jij, j subscript ij into sigma subscript I into sigma subscript j. Now let us come to the next slide, which means now we apply external magnetic fields to each magnet, right? So one external magnetic field, let us say the first external magnetic field represented by this bar affects the strength of the first magnet, the spin strength even, and the second, it can change the spin orientation. The external magnetic field is so strong that it can flip the signs of the spins. That means, for example, the second magnet can flip the south pole downwards and north pole upwards. So that means the strength of the external magnetic field is quite high. But for simplicity, we will assume that these magnets will act on the individual magnets for which these bars or these magnetic bars are placed. Now, how this changes the overall Hamiltonian? This changes the modeling of these external magnetic fields will be done using another by the addition of another term. So that means we will take the strength of the magnetic field and we will take the random variable sigma 1 for the first magnet, that means we will take the product of the strength of the magnetic field and the random variable, individual random variable for the magnet. So we introduce one more term here, which is the index is I, summation of index I. Hi represents the strength of the external magnetic field. Sigma I represents the spin, the strength of the coupling between the magnet 1. Um, Sigma I is the random variable, the spin random variable for the magnet 1. Sigma 1, sigma 2 maybe for the second, sigma 3. So that means what I'm trying to say is the external magnetic field affects only the individual magnets. That is why there is only one term sigma present here with the strength of the external magnetic field. And by convention, we choose the Hamiltonian to be negative. Actually, there is a reason for that. The reason is basically, just let me I will take up the reason maybe a little later. Okay, I will. Otherwise, the basic reason is one way to say negative sign. The presence of negative sign is the convention. The other will say that, for example, if the let's say this. Let me just explain it actually. So if let us say Jij is positive, that means this coefficient is positive, then if sigma I and sigma j have the same spins, that will be called as aligned, right? And if so, therefore the negative sign actually favors the alignment, and when sigma I and sigma j are with the same spin and sigma jij is also positive, the negative sign will make the energy minimum. You need to understand that negative sign is there so that the convention that the system actually settles to minimum energy state should be maintained. That's the only purpose of putting this negative sign, with to explain the physics of the system, in which the system tends to come to the uh, minimum energy state. Right. Now, for example, if the system is trying, let us say this energy diagram is showing that system may settle to a local minima also, but if we use the coupling strength, if we use the external magnetic field, so that can actually take out the system, because we are actually disturbing, we are adding a turbulence to the system. That means we are trying to extract the system, we are trying to disturb the system. In that case, the system can come out of this local minima and can reach to the global minimum. So that's the advantage of the negative sign. Actually, negative sign will take care of the overall situation, in which the idea is that the system should end up with the minimum energy state, right? So this is the actually this equation is the classical Ising model equation, and if this is exact this type of equation is exactly the same kind of equation that we see in computing world, which are actually NP hard problems. So NP, if we try to model the NP hard problems, the overall Hamiltonian actually comes out to be like this. What I mean to say is that the Hamiltonian of the problem, NP hard problems, looks like the Hamiltonian of the classical Ising model. Now we have maintained, we have actually modeled the classical Ising model, so we can use the same equation to map it with the to the NP hard problem, and we can take advantage of this Hamiltonian to further minimize the Hamiltonian and reach an optimal solution. Actually, this situation, the classical Ising model will help in that way, in achieving the minimum energy solution when we do the mapping of the combinatorial optimization problem with this Hamiltonian shown here. Now let me come out of this presentation, and I will okay. So I will, instead of using, I have shown the Hamiltonian or the energy of the classical Ising model. I'm taking here a positive sign for the NP hard problems. So as I said, positive sign or negative sign does not make much difference. Ultimately, we have to reach to the minimization of the energy. Now, what we need to understand here. So modeling the Ising Hamiltonian, I have just explained how the modeling of the Ising model will be done. The Ising model is exactly a system whose energy depends on binary spins and their pair wise interaction. That means low energy is equal to good configuration. If we can map uh, cost of a combinatorial problem to energy of an Ising model, the finding of the ground state of the Ising model solves the original problem. If we are able to find the ground state of the Ising model, that means we have found the solution for the combinatorial problem, right? So in many hard NP hard problems in computer science will give you an equation of energy which actually resembles with the Hamiltonian of the Ising model. Now, uh, instead of sigma, as I used in my presentation, I will use S to represent the spin, right? So this is the energy equation which we will use in our solution of the combinatorial problems. Um, the combinatorial problems do not exactly represent a spin configuration. Please mind it. This S represents the spins in classical Ising model, J represents the strength of the, J represents the wall between the magnets which controls this spin interaction with each other. In combinatorial problems, these terms may represent some different items, but when we try to state the energy of the combinatorial problem, the overall equation that we achieve looks like the form, the structure of the equation, the structure of the Hamiltonian is the same as the Ising model, right? So this is the equation I have just slightly modified for the classical Ising model, in which I say Si belongs to -1 or +1 as the spin at site. -1 or +1 means if you are taking north pole upwards as -1, then south pole upwards will be +1, or vice versa. So that represents the spin configuration, right? Hi is a local field on spin. Hi is the external field that we apply, local field applied on the spin, and Jij is the coupling between spins I and j. So this is, now we have to try to solve the combinatorial problems using this equation. But in my presentation, I have just tried to explain each and every situation where the modeling of this equation is explained, that how each and every term comes into this Hamiltonian equation and what is its importance. Now, for this equation, what is the decision? So it's a decision problem. Is there a configuration S? That means we have to look for a spin configuration S such that this energy of the overall Hamiltonian is less than or equal to the minimum energy of the system, that means the ground state. So that's the problem at hand, and this type of problem exactly matches with many computer science problems. So if you are able to find out the ground state of the Ising model, that means we are able to find out the minimum energy solution for that combinatorial problem. This is the pretext on which we will try to solve other combinatorial problems. I will cover the complete solutions in my further coming lectures. Thank you.